Okay, students, welcome to our introduction video on lesson 14. Also, don't forget we did an overview video as well. Here we're going to describe the content and take it one section at a time. We'll talk about the polynomial functions first, and then we'll talk about the rational functions. Okay, so I have two examples here. The first example is we're making a box, okay, and we want to know about the volume. Well, we know that volume is the width times the length times the height, and if you notice, that's going to give us an x cubed polynomial function, which is very interesting, and we could graph it. It may look a little like this right here, okay. So remember, the function is describing the volume of the box for a given value of x. That is the gist of a polynomial function. Also notice that there's a zero here, there's a zero here. In theory, the graphs keep on going on. Okay, that's called end behavior. And also notice between these two domain values, there's a maximum as well. Okay. Now let's look over on the right side. On the right side, I'm going to show you an example of somebody's walking further and further to the right, and someone's taken a picture of them. They're standing next to this wall. Well, if they kept on walking that way forever and ever, and you're taking a picture, won't the image inside the picture get smaller and smaller? And the answer to that, obviously is yes, it would. So now this graph is a part of an explanation of how that function works. It is a description in a graphical form. So for example, this x-axis talks about the length in feet they walk to the right, and then the y would be the height of the person as measured in the film in the camera. And so as you know, that the further you go this way, the smaller or the lower value the y value would be. It would be positive, but it would get smaller and smaller. Of course, the question is if the road was straight, would the person ever go away? And so that's a no. And will the function value, in other words, the y, will it ever touch the black line? Well, in theory, no. And so this line y equals 0 is a special line in the understanding of that graphical representation of that phenomenon. So that's our beginning. Okay, so now we want to talk about polynomial functions. I got my light kind of giving me problems here. Don't know exactly how I'm going to work that out, but hey, we're moving on. Polynomial functions. Polynomial functions have this form. Notice here, f of x is equal to a sub n x to the end plus blah blah, and then a sub 1 x, and then a sub 0. This is my leading term because the power of the x is the highest. Okay. Also, the last term is my constant. Okay, there's no x value next to that. Also, the powers are integer powers, positive integer powers, and they start at the highest integer or most positive and go down this way. Now keep in mind, this power of the x is 1, correct? So we're going levels above where we were with the quadratic. That was the power 2. Now we could go cubic to the 4. Here's f of x is equal to x to the 7th plus x to the 5th plus 2. Now notice I don't have a term for every power of x, but notice that the highest power is beginning the polynomial function. Over here, the question is, do I have a polynomial function? The answer is no. Now you may say, well, there's a radical 2 there. Well, that's a constant. That's really not the problem. The problem here is that the power of this x is not an integer. Okay? Hopefully that makes sense. So, how about g of x? My question is, yes, it is a polynomial function, but can you tell me what its leading term is? Well, its leading term is 3x to the 6th. What is the degree of this polynomial? The degree is 6. And what is the leading coefficient? The leading coefficient is this value in front of the x to the 6, which is the value 3. So that's a little bit of the gist of a polynomial function and identifying the function. Okay, students, here's a picture of a general polynomial function. And what we want to do is we want to sort of tell all, okay, tell all. First of all, what's the domain? The domain from left to right, well, it keeps going to the left and right, so it's all real numbers. How about the range? Well, you may think it stops here and then it stops here, but the rest of the function keeps going, so that would be all real as well. Generally speaking, odd polynomial functions are all real and all real. All right, let's see. We can call the location where the graph is crossing the x-axis, we can call it a 0. So this tells us that there's 1, 2, 3. This is a third degree polynomial function. Also, this point right here, there's a maximum. It's not the total maximum, but it's a relative maximum. That point, and then this would be called a relative minimum. This is a gist of a polynomial function and some information you can get by looking at the graph. Let's talk about the zeros of a polynomial function. Now that first one actually is nx to the 5th because you have that you have this x squared here, so x squared, x cubed is x to the 5th. All right, but we've got it factored already, so this that 0 would be 0, and this 0 would be 5. Okay. Actually, if you want to get real technical, isn't x cubed x times x times x? And isn't this x minus 5 and x minus 5? I would have a 0, 0, 0, a 5, and a 5. Does that make sense? So this is called, the 0 is called the 0, and the multiplicity is how many did you have. In this case, you had 3 of them. You could just look at the factor. Here, the 0 was 5, and I had 2 of them. Okay? Now, how about g of x? Well, you may say, oh, we have to factor that. So it's x squared minus 1 times x squared plus 1. But wait a minute, we got to factor that again. That's x plus 1 times x minus 1. And then that's times x squared plus 1. Well, this 0 is negative 1. This one's 1. This one, right? If you tried to set that equal to 0, you'd end up with an imaginary number. So you would have plus or minus I, okay? But normally when we're graphing them, we don't use the imaginary numbers, okay? Or complex numbers, or pure imaginary numbers. So keep that in mind. So here the 0 is negative 1 and 1. Okay, now notice in this picture, I want to talk about a few things. I want to graph those functions like real quick, and then I want to talk about end behavior. So let's just do this. Look at these functions, okay? So the first one, we know that that's a line. And we know this is a parabola. And we know this is a cubic, okay? So notice that this graph would continue that way and that way, this that way and that way, this that way and that way. Well, notice there's a couple things we could point out. The first one would be its end behavior. In other words, as x gets bigger, y gets bigger here. And as x gets further to the left, y gets bigger. How about this one right here? As x goes to the right, the curve goes up, right? So that would be as x gets very large, y gets very large. Here, as x gets very negative, y gets very negative. Now, we're going to explain that when I talk about this graph down here at the bottom. But there is a little piece of information I need to tell you, okay? Whenever the factor has a 1, it crosses. It's just a plane crossing the x-axis. Whenever the factor has a 2, 4, 6, it turns at the 0. It turns at the 0. Here it crossed at the 0. Here it turns at the 0. Now, whenever it's an odd and it's greater than 1, it still crosses here, but it kind of scoots, okay? I'm just going to come up with that word, scoot, okay? It scoots across. It does cross, okay, but it kind of scoots at an angle. So that will help you when you're trying to graph. All right, now we want to talk about end behavior. I talk about this, whatever happened to Johnny. You know, if Johnny was basically an upright citizen, he's probably going to do well. Johnny's a criminal, you know, he's probably going to end up in jail, okay? So we're not so much concerned about what's happening to the graph at the origin. We're concerned about what happens way out to the right and way to the left. What this means is if your graph ever heads this way, what that means is as x goes to positive infinity, the y is going up. Okay? So let me say that this way. As x approaches very big numbers, y is getting very big. Now, how would I describe this direction? Well, it's going to the right, so I'm going to say as x goes to positive infinity, but the y is going down, so the y is going to negative infinity. See that? So this direction means this. This direction means this. All right, how about over here? As x goes to negative infinity, y is what? It's going down. So negative infinity. How about this one? As x goes to negative infinity, it's going further to the left. The y is going up. Okay? That's talking about end behavior. And the end behavior is related to the power of the x, the leading coefficient. So please keep that in mind. So someone says, all right, can you give me an example? Yes. How would you explain the end behavior of that function? Well, it's going to have this general shape. I look here, as x gets bigger, y gets bigger. And the other end of the graph is going to look like this. So I know it's going to have this type of understanding. Now someone says, well, what if I did this? Okay, sorry, it's hard to see, but y equals negative x to the 4th plus 10x cubed. You're going to say, well, the 10x cubed has a lot of power. I know, but when the values get big, this leading term takes over. So a negative x to the 4th, well, that's even, so it would look like this. The graph is going to have that general shape to it. So what that means is you're going to use this part of the curve and this part of the curve and follow my illustration or my graphic organizer here to help you understand end behavior. Now, I want to talk about polynomial functions and where they're positive or negative at. Now, what the intermediate value theorem is, in essence, here's how it works. Let's just say I have a function. At 2, it's 1, and at 3, it's negative 2. Would you agree, if it's a polynomial function and they're smooth, okay, that between 2 and 3, it had to have crossed the 0 over here on the right side? And that's all the intermediate value theorem is saying. There's got to be an intermediate value between 2 and 3 that causes the y to have a 0 right there. Okay? Okay, I want to show you something. If we look at this function, which is already factored, right? Don't I know the zeros? Yes, 0, negative 2, and 1. Also, don't I know the leading term? Yes, it's x times x times x, which is x cubed. Do I know the constant? Actually, there isn't a constant there, but good guess. Now, x cubed, well, if it's positive x cubed, it looks like that, and if it's negative x cubed, it looks like that. It's positive x cubed. So the curve is